Okay, so hello. You're in the right talk if you want to learn about StringViews. My name's Marc Mutz. I come from that company that nobody could pronounce, so we shortened it to KDAP. We do Qt, OpenGL, and C++. And in this talk, I will talk a bit about StringViews. So, this talk is a sibling talk to the one I gave a few weeks ago at Qt World Summit, where it was about QStringView in particular, and this is more about general StringViews and StringView in particular. I will recap the relevant parts of the previous talk briefly. For details, you can look at the other talk online. It's online already. Those that pertain to both kinds of StringViews. And I hope to provide a bit more balanced view on StringViews than has been seen on, for example, CPPCon this year. I will introduce a pattern for heterogeneous lookup in associative containers, something that we don't have for the hashed containers yet. And as a technical deep dive, if we have time, I will go basically on, I will continue the talk from Klaus in the previous slot, who told you to prefer free functions from over member functions, and I will tell you how we married the two together because we needed to provide member functions. And as a last point, we'll see how contracts and string views make a magical combination to turn narrow contracts into wide contract functions. So about me, I'm a defecting member of the Church of Emacs. I'm an aspiring member of the Temple of Elements of Programming. I'm the guardian of partially formed state at KDAP. But for this talk, it suffices that I'm the author of QStringView. So what's a string view? A string view is basically a pointer and a length. Pointer to the string data and a length. It's container agnostic. As long as you have contiguous iterators on your container, you can wrap their data in a string view. It's also non-owning. So I pass around string views, but the data is only referenced, not copied. It has most of the const string API. So StringView has most of the const standard string API, and QStringView has most of the QString API, which is const. Unlike string, a StringView may represent a null pointer. And it is a better tool than character pointer and int, as we will see. And primarily, a string view is an interface type. That's what it mostly is. We will see that I also want to use it in the implementation, please. But at the face value, it's an interface type. And a string view's data is const. You cannot modify the character. You can modify the container. You can modify the string view, make it smaller by substringing. And the string view data is not necessarily null terminated. So for that, there are thoughts on the proposals mailing list to see maybe we need a standard Z string view that always has a null terminator at the end, and then we cannot take arbitrary substrings, but only take off from the beginning. We'll see where that goes. So string view as an interface type. So this is the prototypical example where string view shines. We have a function. We want to count the number of x's in x characters in that string. And instead of passing a string type, we pass a string view. So whatever we pass to that function, the compiler will make sure that the lifetime is at least as long as the function runs. So no lifetime issues. And we can iterate over the string view and count the number of x's and return the result. You can also return from a function. And that's a bit more complicated because the function might be a free function, and you may make the error that Nikolai Yusutis showed in his talk of returning a reference to a temporary object. That's always a bad mistake. But in this case, the compiler will not tell you because it does not know that standard string view is a literal type, is a reference type. There are ideas how to fix this, right? Inheriting from ampersand or something like that, but it's not there yet. So in this case, what you need to do for now is you need to document the lifetime of your object that you return of the data that underlies the object. But this solves a very real problem in Qt, for example. We did not name this plugin name for nothing, because in Qt we have the option of creating a QString from static storage data. And once you do this, and that static storage is in the plugin, and the QString is distributed all over the application, and then the plugin gets unloaded. You have a pointer to stale data. And this cannot happen with StringView because everyone should know by the time StringViews permeate our APIs that if you want to store something, you need to take a strong reference and not keep the StringView around. So this might help. This is probably a mistake. Depending on what some func returns, if it's a string, you will bind that temporary return value to a string view. But since, again, the compiler does not know that string view is a reference type, you don't get the same treatment as if you had written a reference, a C++ reference, namely lifetime extension. It would keep the argument, the temporary alive as long as the reference lives. You don't get that at the moment. So this is almost always a mistake. And almost always is also the key to fixing this, because if you used auto, this could not happen. So if you use AAA, this cannot happen. So that's the solution. Use auto. And if you want to make sure that what you got back is a string view, then you cast it. All right. So here R pins the return value, whatever it is, into memory and onto the stack, and SV lives only up to the time that R also lives. Of course, we could return SV from the function, but we could also return R.data. It's the same problem. And the solutions are the same. Namely, if you crank up the optimization, the compiler will probably tell you, or you need some clang tidy check for this. In this case, where we combine the two, it's again perfectly okay. It does not matter what some func returns. As soon as it compiles, it's okay, because the temporary is kept alive by the compiler. So it's also perfectly okay. But StringView is more than an interface type. And here's an example. So this is my first StringView function. I have legacy code. So we're using a standard string here. These are just some helper functions, ignore them. And what we want to check is whether this is a valid identifier. So we first check whether it's a valid first character, and then the remaining ones need to be valid follow-up characters. And of course, you can simplify this a bit, but you will also see that for the loop, you need to use iterators. Right? You could think about saying here, for loop over s.substring1, but this is prohibitively expensive because it allocates in a general case. So you will very quickly come to the conclusion that you best do this with iterators, and as soon as you have iterators, you can have isEmpty, or in this case, .empty, and .front for free by using the iterators that you already have. So the first step is that, down here, you see that regardless of what we feed in there, it allocates because it needs a standard string. So the first thing that we can do is simply replace the argument with a standard string view. And since standard string view has all the const API from standard string, we don't need to change anything, it works. What has changed is the call side, because now we no longer allocate. Oops. Sorry. We no longer allocate, neither here nor there. Because the string view is not owning, it does not allocate any memory, it's just a pointer and a length, and it can figure out the pointer and the length from a const char star. No problem. So it's already better, but we can do more here. So first, we can use the member functions. And these member functions we could have used on standard string 2. We could have called isEmpty and sFront, but indulge me here while we play this game. You will see where this is going. We still need to iterate this for the loop, and we can still write a ranged for loop. But this, now that we have a string view, we actually can. So now we can call substr1 because it's totally cheap. It's like increasing an iterator, incrementing an iterator. It's nothing else to the compiler. And this, I think, is much more expressive than what we could perform efficiently do with standard string. And so yes, if you have a string view, you also want to use it for parsing stuff. This is parsing. So, and we can go a step further. Now that we don't have standard string, we have a string view, we can make everything const expr. And our last line here, or penultimate line, becomes a constant. The compiler writes into the executable cout true. Because it is a valid identifier and can calculate it at compile time. Whether you need this or not, I don't know. But it's nice to have these optimization opportunities that the compiler can find for you. So next nice thing that you can do with string view is you can implement heterogeneous associative container lookup, which you don't have for unordered containers. So, because nobody yet figured out how to ensure that hash functions defined for different types are checkable to be consistent, because you need consistent hash functions for equal elements from the two domains. The hashes need to be equal. That's the fundamental relation between equality operator and standard hash. And it's very hard to make this, to check this. And so we have this for ordered containers, because it's presumably easier for less than for standard hash, but we don't have it for unordered containers. And the question now is, do we need this? And really, no, we don't, because we can do this. So we have a map of string to string, replacements, variable references, whatever, does not matter. And we have this code and we want to improve it. So we have $I as a character literal, works. We have $I as a string view, literal, works. We have $I as a string. I put that onto a separate line to indicate that, yes, this line is throwing or allocating, but this one is not. Oh, this one is not. But the first two are, you always need to construct this standard string in order to look up something like a const char star or a string view. By the way, how many find functions do we have here? How many find functions did we call? Not how often we called it, but how many find functions we have used here. So who's for 3? 2? 1? It's 1. It's always the same. It takes a standard string, and we implicitly convert to the standard string. Right? Just one find function. Now, ordered SDL containers have heterogeneous lookup. And, but we need to manually enable that. And you do this with the diamond-shaped less operator as the comparator. Yeah, right. So now we can say, find me the string literal, and it will not allocate. And you can say, find me the string view, and it will not allocate. And this one did not allocate, and last one does not allocate either. But again, the question, how many functions do we have here? So minimum 1, of course, maximum 4. Who's for 4? 3, 2, 1. The answer is 3 or 4, depending on the quality of the implementation, because we have one function template. Find now is a function template. Okay, there's also an overloaded find, but for the purposes of this discussion, that does not matter. And depending on how good the implementation is, the first and the last line will actually be different functions, because the first one is const char array of 3, and the last one is const char array of 6. These are different types. Yeah, so if the implementation does not actively decay the types and hands it over to some implementation functions, we have created 4 functions here. Can we do better? And Obama is no longer here, but yes, we can. So the first step is to put all the data into the mapped type. In the beginning, we had the replacement and the replacee in different types, and one was the key and another one was the value. Now we need to move all the data into the mapped type, into the value type. And we do this with just a normal struct, replacement, standard string from and to. Now we create an unordered map from StringView to replacement. All right? Replacement contains from and to, it contains all the data. And as the key, we use a StringView, something non-owning. So now we again look at our example, and the first line doesn't allocate, second line does not allocate, penultimate line does not allocate, and the last line also does not allocate. And again the question, how many find functions do we have? Maximum 4, minimum 1. Who's for 4? 3, 2, 1. You got it. It's 1. We're back in the same thing. We did not pass a diamond-shaped less than or something. Well, you cannot even do this in unordered map. But find is back to a normal function, and find takes a string view. But string view can be called with anything that converts to a string view. So we're back to find with one function, and the same flexibility that we had with the diamond-shaped operator. But since we don't require the diamond-shaped operator, less diamond, we now can do this on unordered map, which does not have this feature, or QHash, which also does not have this feature, right? So here's the drawback. When you put something into the map, you have to do a bit more work. So here, we somehow got the replacement map, don't care where from, and we have some parse entity, and it returns me a name and the text. This is C++ 17, it's maybe a pair or a struct, does not matter. And then we need to convert to an owning reference. In this case, it's a standard string. We do this for key separate because we need it twice. Once for lookup and once for actually storing. And for the text, for the replacement text, we do it once here. So we call replacement emplace with the key and move the key into the container. And toString text will produce an R value, so it will also move. Why can I move here? Because the move is only a cast. Standard move is a cast. It does not actually move out. The actual move happens in the function, and by that time the StringView object has already been created, which is implicitly created for the first argument, and therefore this is safe. Is it? It's safe as long as the string does not use SSO, small string optimization. And sadly, luckily, now these days we need to assume that our std string has SSO. And then the code becomes a bit more complicated. It looks like this. So the first 3 lines are still the same up to line 4. And then we say try emplace, key. And for now, we put a default constructed string into the place of the name in the replacement. We'll fix that later. And then we get back a pair of iterator and bool that tells us where and if the element was inserted. And if it is inserted, we need to fix up the key. the key now points to the wrong data. It points to the key we have here stored on the stack in line 4, and if it has SSO, the buffer that it points to is on our stack. And what we moved in to the node and constructed there is another copy. So we need to fix that. And luckily in C++ 17 we have now an API to fix up the key without reinserting or without reconstructing the node. And so we extract the node from the map, making sure not to invalidate the iterator or keeping a copy of the iterator around that is not going to be invalidated. That's what the ++ is for. Then we have a node handle, and we can set its value's name to key. This is what we should have done in line 5 already, but couldn't because we need to keep key around so that the lookup works in the first argument of try and place. And that's the normal assignment operator for standard string, so it returns us a reference, and with that we can convert that standard string to the key, which we do with the first equal sign. And then we insert back, then we have fixed up the node, so the key actually refers to the mapped type, or the map type's data, and then we can insert it back into the map with a hint, so it's 01, it does not need to sort again. So yeah, it's complicated, but if you have a type like a unique pointer or something that does not have SSO, you can use the cheaper or simpler option on the previous slide. So how do you like that? Would you use that in production? Head shaking? Come on, we are C++ experts, aren't we? We're using C++ because we want our code to be fast. You would actually use a standard string as a key in a lookup and incur the memory allocation every time you look something up? Seriously? Well, you need to hide this behind an interface, of course, but as an implementation detail, go ahead, use it. So, this is a general pattern. It's not limited to StringViews. It's just that StringView is the only view type that we currently have in the standard. ArrayView has not made it. So here's the pattern. Given a key type and a map type, which is what you actually want to look up, define the following. Key type prime is a view on the key type. For strings, that's StringView. For unique pointer, that's T star. And for everything else, you need to come up with your own definition. Yeah? It needs to be hashable. It needs to be equality comparable. Once you have that, you have a key type that you can use in a standard unordered container. And the map type becomes a pair of the original key type and the original mapped type. I'm not telling you you should use standard pair for this, even though a generic implementation of this pattern would probably have to use it, but better struct. Standard pair is a monster, and you don't want that monster around in your code if you don't need to. And then you define the map, ordered map or unordered map, over key type prime and map type prime. And you can use find on it, and then extract the original mapped type from the map type prime that find returns you. Completely general pattern, use it or not. But this is what views enable. So, and this brings us to the end of this QStringView talk. And the conclusion here is use StringView as a function argument, freely, without worries. Everything is okay. As a return argument, document the lifetime. And as automatic or member variables, watch out for lifetime issues. And again, here, if you use AAA, you have much less problems with these things than some people have you believe. But then came CPPCon this year. And this guy, who wrote several books on C++, told us that StringView is considered harmful. Never return a StringView. Never initialize a returned value as standard string. Yeah, that is actually correct. That we saw in one of our examples, and I said the fix is to use auto, AAA. But he says on the same slide that AAA is broken with StringView. Okay. Clearly, the C++ community is undecided on this. And I could go on and rant about this because I like StringViews and he doesn't, but on another keynote, we have learned that if you argue, you're losing. So I'm not arguing. So let's look at what his use case actually is. And keep in mind that I'm coming from a classic class library where most of the stuff is out of line, cute. And he just wrote a book with David Abrahams and David van der Voort about templates in depth. So his use case is actually this, still too small, so let's zoom in further. We have this function. Look at the right side on the left side first. So we have a double function which returns x plus x. So the argument added to itself. And his use case is if you use StringViews. Yeah, you have a string view here, SV on the left-hand side, long string view, and you double it, what do you get out? If you look at his options, he uses the same argument type for the argument and the return value. So if we put a string view in, we will get a string view out. And of course, on the first try, we will get a compile error because there's no operator plus for string views. Why should there be? What should be the result? Standard string? Why not standard vector of car? So he needs to define one. That's the red line above there. And if we want to add two strings, we need to return string views, we need to return an owning container because otherwise we cannot hold the memory that we allocated for the result. But then we come to the point that inside double, or DBL, we're adding two strings, we get a QString back, QString implicitly converts, standard string, sorry, std_string implicitly converts to std_string_view, and that is the return type. So we're returning a std_string, a local std_string, as a std_string_view. And of course, that crashes at runtime. But is this a reason to completely ban StringView? I don't think so. So let's have a more balanced case. And if you look around and look at the new technologies, StringView and ranged for and the range proposal, they all have these problems. It starts with if you have some expression templates and you pass in R values, function calls or standard moves, and then you catch it in an auto variable. You're catching the AST of that expression template and not the result. And then as soon as the semicolon has executed, the R values go out of scope and you're referencing deleted data. We have seen StringView. You can also think about a getVector function that returns you a vector, and then you use the range TS to sort it with pipe syntax. And then you want to iterate over the result, and you might do it like that, just with arranged for loops. And the same problem again, the getVector return value is destroyed as soon as the semicolon is executed, which is hidden behind the arranged for loop. And you iterate over deleted data. So this is a general problem in C++, and it needs a general solution. So StringView is not alone in this. We must find a way to solve this problem somehow for all of C++. And then standard StringView and QStringView will just piggyback on the solution, whatever they come up with. For example, inheriting from ampersand to tell the compiler that this is a reference type. And it should keep its constructor arguments alive for the lifetime. Something like that. So one thing I don't like, and that ties in with what Dan Sachs said, I wouldn't want to be told not to use a knife just because if I grab it the wrong way around, I cut myself. So Let's assume for the rest of the talk that the probability that StringViews are harmful is strictly less than 1. So we have a chance of actually having something from the StringViews. So next I want to talk about marrying member functions and free functions. And Klaus Igelberger has told you in the last slot or on CPPCon that you should strongly prefer free functions. He has given a long list of arguments for this. But if you want to make a string view that is a drop-in replacement for the owning container, the owning container starts out with member functions. You have .substring, and in Qt you have .mid and .left and .find, and the same on standard string. So you must provide member functions too. You cannot tell your clientele that, oh, I made this string view, but now you need to rewrite all your code from member functions to free functions. And so how to put these two together? So one of the problems of member functions, I don't know whether Klaus actually touched on it, but for us, when we implemented QStringView, that was one of the issues, is that member functions take this as a pointer. You cannot ask for this object to be taken by value. That's maybe something for the standard, for the next version of the standard. And so it forces the object that you might reasonably keep in 2 registers, the pointer and the length, during, for example, our if is valid statement. You force that on the stack just to be able to call that function, because you need an address, and a register value has no address. And Chandler has shown this some years ago, I think 2013, in one of his talks, where he compares what Clang does with a simple struct which contains floats and doubles and has a compute member function, as contrasted with the same struct which has a compute free function, which takes by value. And if you take by value, the compiler sees value, and you take memory out of the picture, and the compiler can do a much better job. So what we wanted to do with QStringView in Qt was to learn from this. We don't want, if we have an out-of-line function, there are few, like find, which uses SSE under the hood, SIMD instructions, so these are out of line. But for the few functions that are actually out of line, we did not want to incur the penalty that if you call them on a string view, you force the string view into memory. But we can also now not make them free functions because users expect them to be member functions, and member functions force it on the stack. So what we do is, so we need to mirror standard string API. So the solution is to inline the member calls. The inline member function calls out-of-line free functions. So you duplicate the API, at least the out-of-line one, in a private detail namespace. And there you take the string view by value. And the member functions just delegate to that function. And then you have the best of both worlds. You have the member function for people to remember from standard string or QString and type. And the compiler inlines this. You can even mark it with always inline, so the compiler actually always inlines it, even in debug mode. And then the compiler sees, after the first round of operations, sees only the function which takes by value and is happy about it. Right? I cannot speak about the standard implementers. Whether StringView employs this optimization, I can only talk about QStringView in this regard because it's what I implemented, and that one uses this all over the place. So I talked about how this may be something for the next standard. How do we tell the compiler that a member function should receive the object on which it is called by value? And this might be an idea with the equal sign at the end, because we have an ampersand, that is an L value, and a double ampersand, that's an R value reference, and we know equal from lambdas means by value. So maybe, don't know. Or maybe people will see that where's the 0 there for making it a pure virtual function. The first round of feedback on the discussion mailing list was not so enthusiastic about this. But you can see how this is important. You don't want to have two functions that do the same thing. You want to express it in one thing, and you want to force Microsoft compiler. Anyone here from Microsoft? No. To introduce yet another calling convention where they don't put QStringView passed by value onto the stack just because the ABI does not allow for it to be passed in the register. So, last point, contracts and string views. So, what's a contract? A contract is a set of preconditions and a set of postconditions. Some people will kill me now, but this for this talk, this is sufficient depth. And actually, we're only interested in the preconditions. What is a precondition? A precondition is a predicate, and that you can formulate, usually only in prose and not in the actual language. If that predicate is true, you're allowed to call the function. You're calling the function in contract. If the predicate is false for some reason, you're not allowed to call the function. Calling the function would be undefined behavior. And the mere act of calling the function out of contract is already undefined behavior. Time and space stop there and twist back on itself, and 5 minutes earlier you can already have some rocket launched. Standard is very clear on this, that undefined behavior does not start when you execute the undefined behavior, but it starts earlier. So here's an example of some non-trivial preconditions. Standard lower bound, first, last, value, and compare. So the first precondition is that f and l as an open interval is a valid range. And f and l should also be sorted according to whatever CMP sorts after. CMP is supposed to be a strict weak ordering. And the declared type of v and the value type of f, so what star f returns, this is EOP syntax, they should be equality comparable. There needs to be an operator equal defined for these two types if they happen to be different. So, and valid range you cannot check in C++. There is no way you can write C++ code that checks that f and l, that L is reachable from F, and that actually terminates. And you can also not check in C++ whether the elements that are pointed to are actually initialized. I can pass standard begin and standard end of an uninitialized C array, and it's not a valid range because there's nothing in there. I can check that the range, after I've not checked that it's valid, I can check the range is sorted. Adjacent find with compare should return, I think, end. So I can do that, but doing so is violating a post condition of the function, which says I have called CMP maximum log n times, and n is the distance from F to L. And if I call adjacent find, I have called it n minus 1 times. This is O n and not O log n. So I cannot do that either. Maybe in debug mode I get away with it, but introducing something which is n log n usually to quadratic behavior is certainly going to be frowned upon by your clients. I can also not check that CMP is a strict weak order. I can maybe think of exhaustive testing of all the elements. First of all, I cannot enumerate all the elements of a type. And second of all, it will also take much longer than the time budget or the complexity budget that this function has. What I can check is that it's equality comparable on the syntax level, but again, I cannot say that the decal type of V, actually it's not equality comparable. Strike that, it's from a find if. We don't need equality comparable, not for lower bound. So just keep the first three. So we have seen that lower bound has three preconditions. None of them we can check But there are still preconditions. And it's still undefined behavior to call this function out of contract. And calling out a function out of contract, as I said, is undefined behavior. So what about valid parameter values? I want to talk about string views as arguments. So the usual thing comes up when you see the trick that I will conjure up. We will ask the same question, so I'm putting it in the front. What about valid parameter values? Or, as it would be written in EOP, for every parameter p from the domain of the parameter type, the value of p should be in the domain of the type. Yeah? So assume that there exists a parameter p which is not in the domain. Then I say that undefined behavior has already happened because you cannot have legally constructed such a value. The constructor should have prevented you. Or the mere calling of that constructor will have already invoked UB. So that all the parameter values are valid values for their types, that is kind of implied. We don't need to write that on every function, right? And this will become important in a second. So let's compare standard string view and pointer length. And I will magically make a narrow contract into a wide contract. There will be smoke. And there will be, hey presto. So let's look at a function that takes a pointer and a length argument. And we have an array. So we call the function with the array and the size of the array. If the array is initialized, that's perfectly okay, but it's not initialized, so I'm calling fung out of contract. And even though I said it does not matter where UB actually is invoked, it travels back in time, and space and time otherwise ends and warps back on itself, for the time being, just indulge me and play along. Where does the UB here happen? Inside the function, I previously said, as soon as you call the function. Just the mere act of calling the function invokes undefined behavior. Yes, correct. So now we wrap the thing in a string view. Where does the undefined behavior happen? It's still undefined, because the string view constructor is saying, don't construct me over such a range.
At call site. At call site.
At?
Call site.
Of what?
Of fun.
No. We're constructing a QStringView object first. And the StringView constructor says, I have these preconditions, and they happen to be the same as the function, but now the UB happens at StringView construction time. And the function can magically assume that it always gets valid parameter values. You see where this is magic? Another example. We have the character array, we have it initialized, but we make an off by one error. And again, the question, where does the UB happen? As we've called the function. Where does the UB appear here? When we call the StringView constructor. So, now we take this narrow contract function. Everyone understands why this is a narrow contract function? What is a narrow contract function? It's a function that has precondition. Name one precondition, please.
Valid pointer.
Valid pointer, what does that mean? Not null? I can accept not null. Remember lower bound. Yeah, I know that you know the answer. It's the pointer and the size need to form a valid range. Just like with lower bound, we had two iterators. Now we have iterator and length. They're equivalent, right? The range TS has sentinel for this concept, where the end of the range is defined by another type than the beginning is. Oh yeah, so the range formed from the pointer and the length needs to be valid. That's a precondition, so the function has a narrow contract. Narrow contract functions, John Lakos tells us, must not have no except. So this function has no except. And now the magic happens. Imagine you're in the circus, and the conjurer brings up the laptop, serves to the function, and starts typing string underscore VIEW. And hey presto, we have a wide contract function. No applause, seriously. Yeah, as Klaus has already remarked, you're a hard crowd to crack. So, is this, no, here we have the two. One is a wide contract and the other one is a narrow contract function. One is no except, the other one is no except. Where's the difference, you ask, right? We talked the last 10 minutes about where the difference is, but you still ask where is the difference. So, no really, where's the trick? So what you're thinking is, I cannot check this anyway. And the constructor call is inlined, and there is no UB-SAN check for it, and all these kind of things. So they are compiling to the same executable code, probably, unless you're compiling on Windows with that shitty ABI. How can possibly one thing be a wide contract function and the other one a narrow contract function? The second one also needs to be a narrow contract function because it's equivalent. And no, it's not. So you cannot check whether the range is valid in C++. But what if you could? Where would the check be? Just magic invocation. Again, magic. I'm the conjurer here. I give you a way to check that a range is valid from your C++ program. Where would you check it?
Before I call the function.
Which function? Which f that's overloaded? The pointer size would need to call it inside the function, right? Yeah, if you want to check preconditions outside the function, but if you wanted to assert on the precondition, you would call it in the function. Yeah? I don't see because the things are so bright. And in the case with StringView, where would I check it? If I wanted to assert in the constructor, outside the function. So do you see the difference now? And you say, no, because you cannot write this function. And I say, yes, because I can. And with that, I will go back to the slide. I thank you for your attention, and I'm ready to take questions. Yeah.
Hi. Thank you for the talk. I'm really glad I came to your talk because I myself consider myself a StringView enthusiast, and I got a little scared after I watched Nico Josuti's talk at CPPCon. So I'm very glad I came to your talk. I was just curious, what was your experience in actually using QStringView in the Qt library after you've implemented it? Have you started rolling out? I'm not a Qt user, so I'm not aware of the progress. Have you started rolling out QStringView instead of QString throughout your APIs? Did you do overloading? Did you actually replace your APIs? How did you go about doing that? And how far have you reached?
Yeah. So I need to say that QStringView in Qt 5.10 is not complete yet. There's some functionality missing. Splitting, searching. So we cannot use it in many places because usually in places where you would use this, the first thing that the function does is splitting and searching.
Okay.
So, for example, in the XML parser, I have changed the entity lookup to what we saw here with a non-heterogeneous lookup, and that saved quite some allocations and text size too. I have not benchmarked that because for me it's enough if I save allocation, I know it will be faster. I don't need a profiler.
I was more curious along the lines of using the APIs, not on the performance side. I was curious about how the community or the users of the code actually embrace the change, and did they find any breaking issues in their code as a result of the API change?
So,
any surprises there?
It's Qt 5.10, and Qt 5.10 is not out yet. So,
so it's too early.
It's too early to tell how normal users are experiencing this. I'm hoping with my talks to kind of prevent mistakes such as Nikolai trapped into or warned about to happen, and the documentation also reflects this. But I'm also pretty sure that you cannot foresee all the traps that people fall in, and so I'm actually interested in finding out what real-world use of this will be. So far, my experience with it, using it inside Qt, but I'm biased, I'm the author, I know the pitfalls, has been pretty good.
Cool, thank you.
You're welcome. Other questions?
Hi, thank you for your talk. In another talk, there was an example regarding StringViews where the combination of a new API with StringView and combination with functions that use strings actually leads to more allocations because of the interface needing this. Was this a practical problem when you did the implementation? How did you treat it? Did you have to double all the functions, the low-level functions?
Yeah and no. So yes, if you replace a function that previously took a QString, for example, with one that takes a QStringView or standard StringView, you may incur more or less copying by how you use it. One of the things that Nikolai said, don't put a QString, standard string at the end of a standard StringView chain. And but more often than not, you keep the old code working, and it's calling the function that it previously called, and so the complexity is the same, and the number of allocations, and you just enable more ways of calling the function. And in Qt, we made very, very carefully sure that you can overload a QString and a QStringView function at the same time, and there will never be an ambiguity. And you don't have that with standard string. They both take car literals, so you cannot overload them and assume no ambiguity calls. So you cannot really do this, what we're doing in Qt, with standard string and standard StringView, because they don't overload as well. But the idea is that by providing another overload, you enable more ways to call the function and not change the existing calls. Does that answer your question?
Yeah, but in the end you have to duplicate code then.
You have duplicate code. Sometimes you can, out of line, make the owning container function call the non-owning container functions. If you're interested in that, it's all in the other talk. It does not apply one-to-one to the standard types because you cannot overload them. But for Qt, that's discussed in detail in the previous talk on Qt World Summit.
Okay, thank you.
You're welcome. Anyone else? If that is not the case, then I thank you for your attention again, and have a nice